Hello, can you guys hear me? Can you hear? So let's wait another minute. Oh, okay, good, Renato. Thank you. So week 15, Friday again. And do you guys feel exhausted? I don't see a lot of people in the office hour. Very. Me too, yeah. So we are in the end of the semester. So we have next week left. As I promised, I'm going to show you the final exam of last year, next Wednesday, okay? So today we are going to continue our discussion on the actuators. So welcome to week 15, lecture B. So today we are going to cover let me do a little bit on this. Okay. So we are going to talk about, last time we talked about brushed DC motors, okay? Brushed DC motors. I hope everybody will feel comfortable about this type of equivalent circuit. So this is the rotor, armature, then have a shaft linked to your load. On this side is called field excitation circuit. And this side is armature voltage, the armature current, and so on. So, but how we really control the speed of the motor? So there are two ways. One is called armature control. You don't touch the field. Another one is called field control. Okay, field control. So basically, we have two types of control. One is control the position. Another one is called speed. Okay, speed control. Both of them are called motion control. Okay, these are the very fundamentals for robotics, for autonomous vehicles. Okay. So we're going to see this picture. Okay. So you have a DC motor system. Okay. So this is the armature current. This is the servo amplifier. Okay. So this is your reference input. So then sometimes you also do a torque transmitted control. You need to control the torque. Okay. And you have a torque sensor. Then this is a tachometer. And this is a potentiometer. It's a pod. It's a potentiometer, or RVDT, to the angular position control. Okay, so that is our typical DC servo system. Okay, DC servo system. So of course we didn't show all those power supplies. Okay, so that is a block diagram. This is our also block diagram in the transfer function form. Okay. So basically your shaft with the load is called load torque, okay, load TL, okay. Then you generate magnetic torque is TM. Then you go through the rotor dynamics. So this is omega coming out, okay, omega coming out. All right, so this is the back EMF. This is your input. So this is our whole motor system. So this is our G of S from this block. So let me do this. So this is the block. The whole thing is our motor system. So in a motor, so basically you give a VA, armature voltage. If you change that voltage, your omega also will change. But our ultimate goal here is to make the omega here to rotate at the speed of set point. So we put set point in here. This is my set point. So I compare to my measured, okay? This is my measured. This is a sensor. So what sensor to use for the speed is called tacho. It's a tachometer to measure the speed. So you feedback, there's an arrow in here. And with this arrow, we put the controller in here, okay? So if the omega d, the desired omega is a constant, how to make the E, like ESS is E infinity is 0, equal steady state arrow. How to make it 0? We talked about it, right? So internal model principle or system types. So you have to have an integrator in here, okay, like KP times E or KI times integration of the E. Okay, so this is called PI control, your controller signal. The control signal is U, and the U is actually my VA. Okay, the VA. Okay, the U is output of my controller. Okay, then my controller will give this V in here. But there's something missing in here, I want to tell you. So you cannot directly link the output of the controller direct to the motor as an amateur voltage, like we added in amateur voltage in here. This is my amateur voltage. So we cannot directly use that. You need to go through something called power amplifier. So you got a U in here, is a controller signal. Then this is the VA, okay? But usually we treat this power amplifier as a 1, okay? 1-to-1 relationship. So we usually ignore that, but you should know physically there's something here. It's called a power amplifier. Otherwise, don't have enough power to drive the motor, okay? So block diagram of field control current is like this. So you have a rotor in here, magnetic torque in here, electromagnetic Ka in here. This is the field, IF, okay, IF, the field excitation current, the field circuit. But remember, this field circuit, LF divided by RF, is very small, less than the GM divided by BM. It's much smaller than the time constant. So this thing actually can be deleted. So this dynamics is ignorable. So it's like a constant. Okay, it's a constant. So that's why in many of the applications we say that, oh, I got a voltage in here, then you produce my omega, then you get the integration, then you got a theta. So what's inside here? Inside here is K is a gain, T is a time constant, S plus 1. This is approximation. This is approximation because in this case, so you put a controller in here. So you do a feedback control like this. You can see what was missing. This one is actually ignored as a constant. Okay, this constant can be lumped into the C as a gain. Okay, it's combine them together. It's called lumped together. Okay, so that's a field control motor. So again, there are two ways to do the speed control. One is to change the VA. One is to change the RF. Okay, RF. So there's also another way to do is called PLL, the phase locked loop. Okay, PLL, phase locked loop, phase locked loop. Using that one to do this digital control. Okay, so basically you have an encoder and you have a command. So we want to make sure you synchronize with this shaft encoder, synchronize with this reference power strain. So if there's a phase shift, there's a arrow. This arrow is used to drive that such that it's synchronized. Then this one becomes a 0. Okay. All right. So it's kind of like the phase synchronized. Okay. Synced. Okay. Synced. Synchronized. But they call this is phase locked. Okay. So this is a phase locked servo. Okay. So here's the part we haven't gone through. It's called gear ratio. So in practice, the gear ratio is not chosen arbitrarily. It would be better without gearbox because gearbox is mechanically a weak point. Okay, eventually the gear will get worn or it's too old. You need to replace it, or it could because of shock, you could break the teeth. Okay, so this small teeth here, you can break it. Then you can hear the gearbox becomes noisy and noisier. Okay, so it's better to not to have this one. So then that kind of drive is called direct drive. Okay, direct drive is much harder. Okay, to control, and so we'll see. Okay, why we need a gear ratio. Okay. So the gear ratio is basically to reflect, okay, it's like, so this is your magnetic torque. So this is acceleration. So this is a moment of inertia, okay? So the J2, okay, let me go back. The J2 is the load, okay? This is the load. This is the motor, okay? This is the motor. So you can lump everything into the load side. So then J1 is like N squared. So you have N squared. Like you have a much larger moment of inertia, okay, to reflect to the load side, okay, load side. So this is known for quite a while. And so why we need to study about this gear ratio N in here, okay? So that is, I want to maximize of this. This is acceleration. Acceleration. I want to maximize the acceleration. So I want to see what is my best N, okay? So I do DDN both sides. So I set to 0. That's my stationary point. So then by doing this, we are going to solve the N optimal is actually J2 divided by J1. So the inertia of the motor rotor is equal to the actual load inertia. So that would be optimal. So if it's direct, if it is direct coupled, okay, N is 1, which is not true. J2 is usually greater than J1, okay? Okay, your load has a much larger moment of inertia. So in this case, better you have gearbox, okay, gearbox. Otherwise, because of this one, the torque will not be able to directly drive the load. So it's kind of like torque amplification, okay? Especially when you have a linear speed torque curve like this. So if you don't have a load, your speed can be high, okay? Okay, so if you have a very large torque, then your motor simply cannot make it turn, okay? You got stuck in there. So it's called stall torque, okay, stall torque. So usually your system will work on this load power point B. So you have a different load power point, okay, power point, okay. So then you will see that there is also a power curve. The peak power is here. So you better to make this whole system working at a higher power point. So therefore, your torque of load should have a reasonable range, okay? A reasonable range. So you cannot put too high torque, too low torque. So too low torque meaning your power is so small, okay? So you need that kind of trade-off. I think I said all these points. So last thing we should say about brushless DC motor, when you choose one, then you should consider a few factors, okay? So how much torque you need, how about your load characteristics, okay? And how much speed you need. So you need to know where is your operational point, okay? Where is your operational point? So your operational point is here, okay? Or somewhere here, okay? So it depends, okay? So you need to search on this line, in fact, okay? So with that, there's two information you need from your application, torque and speed, okay? Then you go to the motor manufacturer's data, okay, available for these. So two types. One is mechanical specs and also electrical specs. We're going to see next page. So for mechanical one, you need to know mechanical time constant. That is related to the moment, the J2, okay, the J2. Sorry, J1. J1 is your motor, okay. Speed at the rated load, okay. Rated load meaning it's allowed. Usually you work on that load. Rated torque, okay, and friction. This is BM omega. Dimensions and the weight, of course, okay, and no load speed. That's the no load speed is here. This is a no load. The maximum, this one can be this fast. If you need something beyond that, that's not feasible. So all these are called mechanic specs. No load acceleration, d omega dt, rated output power, armature moment of inertia, damping constant, and so on and so forth. For the electrical specs, you have RA, remember? This electrical specifications, electrical time constant, armature resistance, inductance. Drive circuit specs, like voltage current, how big is it? Input power, and field excitation, RF area. So all these parameters, they will give you in this specifications. And also, of course, brush life and motor life, they will give you a specification on that as well. Also, heat transfer and shaft coupling method. There are different ways to couple the shaft versus the load. Efficiency, mounting configurations, different ways of mounting options, and temperature and humidity, perhaps. Okay. So these are the explanations. Okay, so we can quickly go to that. So we have seen this already. Of course, final value is cost, okay? It's cost. So you have a rough idea about permanent magnet DC motor can be at 10,000 RPM, okay? Okay. If you have something much higher, a faster spin, so you probably need to use brushless DC motor. Today we are going to explain that, okay? So for most of the drone applications, okay, they are using a brushless DC motor. So I'm going to tell you that brushless DC motor is called BLDC, okay? BLDC is a brushless DC motor. Brushless DC motor is actually an AC motor, so alternating current motor. It sounds so weird. The reason we still call it a DC motor is because it behaves like a DC motor. But the inner working principle is actually an AC motor, okay? AC motor. I'm going to explain to you after this. So a lot of trade-offs when you make a decision which motor to buy, okay? So usually permanent magnet DC motor is perhaps lower cost, okay? And if you use shaft encoder, the cost is also not so low, okay? But if you use a stepper motor, okay, and brushless motor, usually that is more costlier than the brushed motor. So brushed motor actually is a lower cost solution, okay? But of course, the disadvantage is you need to have a commutator, you need to have a brush. So for brushed motor, you have brush. This brush has some limited time, lifetime, okay? And also there is something called arcing, okay? So if you have something wrong, so then it will induce some arcs in between the brush and the commutator, okay? That arcing can be dangerous if you are working in an environment that the air, surrounding air is dusty or explosive, so it's not safe. Say for example, underground mining environment, underground. So this arcing can be disastrous. So that's why there's some safety issue using a brushed motor. Okay, so I think we finished the brushed motor side. So go back. We discussed a little bit about elementary the DC machine, and then we talked about the winding a little bit. It can be very complicated if you have a multi-pole, okay, that's rotor windings, okay. But however, I hope you only focus on exterior characteristic like a voltage or torque equations, using that equivalent circuit. For excitation, so you have 4 different ways to connect separate winding excitation, and shunt connector, series connector, and compound, okay? But to be honest, I never really used a compound DC machine so far. I heard about it. So most commonly used is a separate winding excitation, okay? We talked about block diagrams, transfer functions. I think it's enough you know that you have omega, then you have, you have a voltage. You have a voltage, then you have omega. So this is a DC motor. And you have a first order system in here. So this is a very simplified one by ignoring all the excitation time constants, okay? Because in reality, that time constant is much, much smaller, okay, than the constant of your mechanical time constant there. We talked about optimal gear ratio. The idea is to have omega d omega dt, and to have a maximum angular acceleration for ddn. So this one to 0. Okay, we are going to have that so-called optimal gear ratio. Okay, optimal gear ratio. Then talk about selections. Okay, briefly. So that's what we have, and now today we are going to do. Actually, I have hydraulics and pneumatics. We don't have time, so but let's focus on the brushless DC motors. It's called BLDC. BLDC. Okay. So although it's very small and now it's getting cheaper and cheaper, and So it's something like this. So you have a BLDC here. So you control it. So you have 3 phase usually. So then you have a ESC. This is called electrical speed control. Electronic speed control. Okay. So all this logic will be generated in here to excite the BLDC. And this is your V, okay? This is your omega. And if you, this one. So if you put this one here, okay, the characteristic from V to is same. It's almost the same, like K and TS plus 1. So it looks like a DC motor, okay? So that's why this is called brushless DC motors. It is actually not a DC motor working principle. It's a totally different working principle inside. But from outside, they look like a brushed DC motor, like brushed DC motor characteristics. So by using this one, ESC control the BLDC. Okay, so why I need 3 phases here? Okay, so to understand that, the first thing we need to understand is called this thing called rotating magnetic field. Okay, magnetic field. So the idea is, okay, so if I make the magnetic field rotating, then that magnetic field will be able to drag the rotor to start to rotate, okay? So we are going to go through that understanding of the rotating magnetic field. So we have different types of AC motors. So this is called AC motors. One is called reluctance device. Another one is called induction motor machines and synchronous machines and PM devices, permanent magnet. So we actually are very interested in the PMLM, okay? It's permanent magnet linear motors. So the motors can go linearly, okay? So PMLM is that, okay? So all these are the AC motor principle. Then after that, we'll mimic the DC, how we can do that. So we start with very simple 2-phase permanent magnet synchronous motors. So then we check the voltage equation, check about torque, and then time domain block diagrams. So you will see it's different to this thing, okay? It's different to this. This is a very simplified version, okay? All right, so let's begin. Let's begin. I know it's in a short time to understand the AC motor is difficult. For me, we learn motors, okay? We learn DC motors for 1 semester. We learn AC motors for 1 semester, okay? 2 semesters dedicated on motors when I was a student. But today, perhaps you don't really need to learn how to change those windings and fix something wrong with the windings. If something wrong, just throw away and get a new one. But however, you should understand the working principle, the foundation of this DC motor and AC motors. So let's try to talk about what is considered as a rotating magnetic field, okay? So in a DC motor, we have a stator, we have a static stator, and also there's a rotator. So DC machine, you have windings on both stationary and rotational members. Okay. So you know that. So we have windings for one is on the so like this. So you on the field side, you have this. Then in the rotation side, armature side, you also have this. So this is a VA, this is VF. So that is our DC motor. You have separate windings on stator and rotor. Okay. Then you have a commutator. So you have a commutator. Okay. So that rotor windings, we can do the magnetic motive force produced by the current flowing in the rotor windings. Okay. So the rotor windings appear to be stationary magnetically. Okay. The constant current in the field, stator winding, the torque produced and the rotation results because of the force established aligned to the two stationary orthogonal magnetic fields. You do so you should understand this way. It's called cutting the magnetic flux. Okay. Okay. So that's the basic principle to convert mechanical energy to electrical energy or vice versa. Okay. So now we are not talking about DC anymore. Okay. If we don't talk the DC, so these devices, it's a winding arrangement of the stator is changing, it's not constant. So also we switch the current in such a way we can produce the rotating magnetic field. Okay. So we are not going to do this a lot. Okay, like you change the winding. Okay, change the winding something like this. Let me show you. Say for example, you have a 2-pole single-phase stator winding. Okay, so again you have 3 windings. Okay, like you have the dot is getting outside, coming outside, out of the paper. Cross is inside of the paper. Okay, so if you put in, so you have this windings here. Okay, so this one is right here. So because of you have this winding, okay, so the magnetic field could rotate. Okay, could rotate. So that's why this is a total magnetic flux. Then this is a phi of S. It's a rotating magnetic field. Okay, so this rotating magnetic field produced by the stator, because of its rotating, it will drag the rotor. Okay, it will drag the rotor to rotate. Okay, to rotate. So that's a basic idea of the AC motors. Okay, AC motors. So you also can make it more. So like elementary 2-pole, 2-phase stator winding. So the reason, let me go back to the one, a 2-pole single phase. Okay, so so you have two parts. Okay, one is this side, one is this side. By getting the alternating current inside, so then your magnetic field is changing. Okay, it's rotating as well. So the magnetic field is time varying. You can make this one like 2 phases, okay, and stator winding. You can also do this rotating magnetic field. So in this air gap inside here, this is the air gap. Inside the air gap, there's a magnetic field that is rotating. Because of that rotating magnetic field, your rotor inside will start to move, follow this rotating. Okay. Sometimes people use the winding arrangement instead of using the supplying voltage. they make that distribution sinusoidally distributed. So let me show you a picture. So they can see they have some windings more, 1, 2, 3, 2, 1. Then you have you do this type of sinusoid approximate. Okay, so therefore you also form this type of rotating magnetic field. Okay, so let's keep going. Right, so yeah. So this is a sinusoid approximation of the winding amount of turns. So you can imagine that will cost more money when you have this kind of variable number of turns for different position. Okay. Okay. I don't see this one very often. So now they do a uniform. What if I have a uniform distribution? I still want to do a magnetic field that's rotating. How we should do that? Yeah, we try to change the supplying voltage inside that. Okay, that's exactly here. We need this called ESC. This is the control logic, all integrating the circuit. Okay, so that the phases, okay, the phases provided the brushless DC motors will generate this magnetic field that is rotating. Okay. I think this is two phases. If you don't feel you can understand, it's okay, don't worry. So you only you need to remember is BLDC is AC, is AC motor. And DC motor is you have a field and armature coils, okay, coils. But in the BLDC, you only have coils on the stator, okay? And this is the stator. And this is the rotor inside. And actually, sometimes the rotor can be outside. Okay, I'll remember to mention that to you later. So let's go. So that's why you need a 3-phase in this case. Okay, this is the 3-phase. So they have a 120 degrees apart. Okay, the phase apart. So with that, they will have this alternating rotating magnetic field. Okay. So reluctance machine, single phase, 2-phase. So again, you can see that in a rotor, in a rotor, there's no coil, okay, and no coil, okay, no windings, okay. It is just a rotor. How to make this rotor rotate? Okay, how to make this one rotate? It is depending on your magnetic field, how you make the magnetic field rotate. Okay, rotate. So using this rotating magnetic field, and because it is a small bar like this, so when you're at a different position, your reluctance is different. So then it is always drag you to a position with smaller reluctance. But once you rotate it, then your phase is also changing. Okay, your phase is also changing. So therefore, you keep moving. So you keep moving. Okay, you keep moving. Then your motor start to rotate. Okay, so that rotate is because of the seeking the smaller reluctance. So therefore, they call this the reluctance machine. Okay. There's also something called induction machines, okay? Induction machines, you have two. 2. So So rotors of both devices are identical in configuration, but the two-phase you have some orthogonal windings, okay, orthogonal windings, sinusoid distributed. Let me see. Yeah, it's nice to see this figure. So now inside here, you start to see the induction machine. You have windings in the rotor, okay? Rotor. You have also the windings. So by changing the winding in the rotor, you also will be able to produce the motion, okay? Produce the motion. And again, you have a rotating magnetic field, okay? And synchronous machines. This usually, oh, it's too much text. I don't want to, I just want to show you some figures, okay, some figures. So synchronous machine, that means you have two rotating magnetic field, okay? So they are at the same speed, okay? Same speed, synchronous. So this is the one we need to pay attention. That means I have a permanent magnet, okay? So usually we replace the rotor, okay, with a magnetic rotor. So the rotor has permanent magnet on it. So this is called permanent magnet device. The basic idea is the same as synchronous machine, okay? So that depends on the strength of the rotor field, or the magnet is not controlled, okay? It's fixed, okay? So it's not used, commonly used for generating power, okay? It's not used that. It's widely used as driving motor, okay? So in fact, there are some differences between the motor. When we say motor, that is, you give electrical power, I give you mechanical motion. But if you call it a generator, is you have mechanical power, you generate electricity. Okay. And also the permanent magnet motors used as stepper motor, and also in the brushless DC motors. So we have a general picture of AC motors. Okay. So AC motors basically is having different ways to produce a rotating magnet field. Okay, magnetic field. Okay, and so for the rotor, for the stator, you have those, but for the rotor, you could have coils. You may not have coils. Okay, so if you don't have coils, that's a reluctance. Reluctance motor. So this is inductance. Okay. So for permanent magnet device, okay, so everything inside in here, this is a block of permanent magnet, okay? So they have a dedicated S and N. This is a fixed position, right? So of course, you know that whenever you have N and S, so it will if this is N, let me see, if this is S, then it will push this S away, right? So then, then if this is N, so this will push this one away. While you reach to here, then you suddenly change this. You change the direction of the current. Then you come over here. This S come over here. Then you will S. This becomes S again. It will push it forward again. So by alternating the magnetic field, so this permanent magnet will keep moving, okay? Will keep moving. So that's the working principle. So this probably is easier to understand about this rotating magnetic field concept. Okay. So let's go through this one slowly because this is BLDC is the most commonly used motors we are using today. So we learn in the permanent magnet brushed DC motors, we have brushes to transmit the power to the armature winding. Armature means a rotor. So then I told you, you may have this arcing danger. So it's a problem. And as time goes, this brush will get excessive wear. So because of that, people have been thinking about, can we remove this brush? So it turns out possible. We just say use brushless motor and having the same, enjoy the same characteristic like brushed DC motors. So that is called a brushless DC motors, overcome these problems. So instead of using mechanic commutator using brush, they use electronic commutation for the conventional mechanic brush commutation. Okay, commutation meaning you change the direction. You suddenly change. You go this way, then suddenly go this way, right? So remember, you have this one, you have sinusoid. If you don't have a brush, you go this way. But you have a brush, you come over here, the brush will turn you to this way. Okay. Okay. So this sinusoid will go this way. So the electronic commutation, they can exactly duplicate the brush commutation like in the conventional DC motor. So the brushless DC motor will have the same linear torque speed curve. So this speed, omega, is the torque. Okay. So this is called no load speed. Okay. This is called stall torque. So meaning omega is 0, you got stuck in there. So that's why we call it the DC motor characteristic. And this characteristic is also called external characteristics. Okay. So why we do brushless DC motors? How we achieved that is because we have that ESC. Okay, ESC. So this is the motor. So you need to have this. Okay. Then you have a control signal here. Okay. Now in drones, they say this is a throttle. Okay, this is a throttle signal. Then this is the speed, RPM. Okay. Okay, but how this is working? That this is the ESC part. They already commercialized everything. So it is so simple, also reliable. Okay, today and cheap. So high reliability is the first consideration. You keep using it, okay? It's indefinite. Okay. So what's the weak point then? That will become that the ball bearing. The bearing failure is the most like the weak point. It is not noisy. It's because of this contact of this brush versus commutator ring. So the BLDC is quiet, okay? So because there's no mechanic friction from the brush, okay? Another thing is high speed, okay? I told you that for brushed DC motor, you probably only can do 10K RPM, okay? 10K RPM. But what if you need another 10 times, like 100K RPM? No way, you have to use brushless, okay? Brushless DC for very high speed, very high speed. Okay. Another characteristic is called peak torque. So sometimes, especially in a drone, sometimes you need a lot of throttle to move away from some like obstacles. So you need the big torque, okay? So the brushless DC motor, they have that windings on the stator housing, okay? Stator housing. So the moving part, okay? The moving part can be lightweight, okay? So you have efficient cooling, and so high current is possible, okay, in the frequent start-stop operation. So for the brushed DC motors, brushless can be like 10 or 20 times higher for that, okay? So that's for the peak torque. Maximum power per unit volume is 5 times higher than the traditional brushed DC motors. So everything is good. What is the disadvantage? So that actually is changing. The brushless DC motor, the most expensive part is the electronic speed control, that block, okay? But right now it is getting much cheaper, okay? Okay, so this probably is no longer so true, okay? And the choice is also restricted. You don't have like brushless DC motors, you have so many manufacturers, so many choices. So those are the disadvantages. So what are the types of brushless DC motor? So the windings on the stator and the rotors is inside, okay? Okay, so in this way, this rotor has smaller inertia, okay? So for the start-stop operation, so you have a start and stop, frequent start-stop operations. So that is called, this is actually called an yin runner, yin runner. So basically you have stator outside, you have rotor inside, okay? So this one will move. This is stator, okay? Stator is outside, rotor is inside. But there's another interesting thing is the windings is on the stator. The rotor is outside, okay? Rotor is outside. So this is good for constant load, high speed applications, okay? So lots of the drones, they are called outrunner BLDC. It is outrunner, okay, outrunner. So for horsepower control motor, so this small horsepower is also called fractional horsepower. So just for your information, your car is about 200-300 horsepower, okay? So for something less than 1 horse, so it's called fractional horsepower motors, okay? So that is usually good to use a brushless DC motors. And usually it's made by a permanent magnet synchronous machine, okay? So you supply from a source, the frequency of which is always equal to the speed of the rotor. So if this is AC, of course, source is the AC source, okay? So the source is a high frequency, then your rotor is this frequency, right? Becomes a brushless DC motor, not because it looks like a DC motor, but because of operating characteristic, external characteristic. looks like brushless shunt motor with constant field current. The field is constant. Okay, it's like permanent magnet brushed DC motors. Okay, so here's the hard part. Like when I was a student, this is not matured yet. So it's considered as a very high-tech research question. How do we supply the permanent magnet synchronous machine from a source frequency which always corresponding to the rotor speed? How do we do that? Okay. So you need to synchronize that. So first, you need to be able to measure where is your motor's position. So most often this is sensed by a Hall effect sensors. Okay, using the magnetically sense the position of the rotor poles. Okay, rotor poles, you will be able to sense where is the position. Then you make this frequency of the source corresponding to this rotor speed. Okay, so you need to use a DC to AC inverter. Okay, where the transistors are switched on and off, the frequency corresponding to the rotor speed. So at this point, I need to open my whiteboard. So to give you a very small, lecture about. So you know that this is your wall outlet. You have AC, right? 100 watt, 60 hertz, like your wall outlet. So this is AC. So you have a cell phone, you have a charger, so you have a block. So you insert this one, you basically do this AC to DC, okay? This is called power converter. You convert AC to DC. Sometimes this is also called rectifier. Okay, rectifier. You rectify the AC to the DC. Okay, so from AC to DC, yeah, there are dedicated techniques, a lot of ways to do that. Okay. But if you go to Walmart, you can buy a box. Then you put, say for example, in your car, you have 12 volt DC plug, right? So then there's this box will have 120 volt. So from DC to AC, this is called inverter. Okay, inverter. So if you go to the Walmart and you want to say, oh, I want to buy a DC to AC converter, people will get confused. Converter means AC to DC. From DC to AC is called inverter, okay? Inverter. Okay. But the life is different. So let me tell you something more. That is called, we haven't learned. So we probably know this type of AC to DC stuff, okay? But do you know that DC can also go to DC, okay? Say for example, I have 12 watt DC, okay? I want to go through a box and give me like 24 watt DC. But of course, you can stepping down is easy. 12 watt, you want to do a 6 watt DC. You can use voltage divider, right? But in a voltage divider, you always have current flowing in this one. So you have 12 watt in here. So you have in here. So you're stepping down, if we do this, then you have load effect. Even if you put the op amp in here, you still have power loss, always convert this power into heat, you get out. So it's not efficient. Stepping down is not efficient. So when stepping up, how? I'll explain to you later, okay? But I hope, yeah, you should also know that from AC also to AC. So say for example, you have an AC with same AC, so you can do what they call transformer. So you have something like this, right? Did you remember? So these are called the electric materials. Then you have something come over here. So this is so then you have so say for example you have get out. So obviously this turns here N2 and turns here are different. So the V1 and the V2 will be different, right? Okay. So this is called transformer, okay, transformer. But remember, when you transformer that, this is 60 Hertz. This is also 60 Hertz, okay? It didn't change much. No, it didn't change the frequency. So in this case, it's called variable voltage, but it's a constant frequency. But what if I need something called a variable voltage and a variable frequency? Yeah. So I need something like 100 Hertz or something. I need something, a power supply, say for example, I need 1000 Hertz power supply. That's useful in sometimes, say for example, in using the AD current, use high frequency to heat up some metal and melt it, okay? So you need that a power supply with very high frequency and with high power. But we probably don't need a 100 watt. We need to change the watt. We will be able to change the magnitude. We'll be able to change the frequency, VVF. Okay, so this is also very useful in industry. It's called AC motors, VSR, variable speed, VSM, variable speed motors. Yeah, variable speed motors. Sorry, VSD. I'm sorry. Yeah, VSD. You can check it. VSD, variable speed drives. Variable speed drives. So at different situation, using different frequency will make the motor more efficient, okay? More efficient. So this is a dedicated course on power electronics, okay? You need to learn all these things. There's dedicated course called power electronics. Unfortunately, we don't have one here. We are trying to establish one, okay? So just for your curiosity, so if you want to step up the DC, what are you going to do? So you can buy a DC-DC block, called DC-DC block. So basically you have a DC, you have a DC in, you have DC out, okay? DC out. Inside is very complicated stuff. You don't need to care. But you need to know how it works, okay? How it works. So if you buy, so I gave this is 5 watt, can be 12 watt DC. What happened inside the box is like the following, okay? So first of all, you have DC here. You do a chopper circuit. You chop it and modulate it in such ways like AC, AC. Chop it. It's AC. This AC with probably with a frequency, okay, F0, okay. With this AC, okay, Then you do transformer. Okay, so then you get another DC, right? Okay. Then this another DC here, you do a converter. Then you do a DC. DC1, DC2. Okay. So that's what's needed. So that's why usually in this transformer, okay. So you may say, oh, I don't see a transformer, but remember that transformer can be very simple, like a magnetic ring, and you do very small amount of coils. Can be very miniaturized. Okay, if F0 is high. So if F0 is low, then you need a big transformer, but now it's a smaller transformer if your F is high. So when you buy the AC/DC block, you need to check what is the chopping frequency. Okay, the frequency higher is more expensive and it's more efficient also. Okay, more efficient, more expensive, of course. Okay, so then the power loss in between is smaller. Okay, yeah, this is your box in here. All right, so DC-DC can be this thick book about all the techniques in a DC-DC converter. Okay, DC-DC converter. So hopefully you are going to have a picture here so you understand everything about this. So from that, you know, how we can do this DC to AC inverter. Okay, the transistors, we use the switching power electronics switching circuits, do the on and off at the frequency corresponding to the rotor speed. Okay, but today it was very hard. But today this is already mature and encapsulated into a small chip. It's called ESC. ESC. And we assume that we have the sinusoid balanced with the same angular velocity as the rotor speed. So you can predict the predominant operating features of the brushless DC motor without involved details of those inverter, okay? Those inverter. So let's see how we can explain. Oh, let's skip this one to the voltage equation and winding inductance. This all looks similar, we have seen it. So lambda is the flux linkage, okay? And we come to machine equation in rotor reference frame. We can put in a matrix form. Oh, that's, so anyway, so we are going to get to this. This is familiar form, okay? So this is a viscous damping. This is our acceleration, angular acceleration. This is the moment of inertia. This is TL is my load. Okay, TE is my generated torque from the motor. So let me see. This is brushless DC motors block diagram. It's very messy. Oh, yeah. So this is something we can explain to you. So basically you have a transistor circuit. So basically you have 6 different phases, okay? So then this is electronic speed control, ESC, okay? And this is with all the digital commutation logic. Who should turn on first, who should turn on next? So then they will produce rotating magnetic field, okay? So when you, that's why I put 3, 1, 2, 3. So if you buy a brushless DC motors, you only give this 3 terminals to you, okay? Then this part is just the ESC, okay? So I think we are getting to the end of the brushless DC motors. Again, the characteristic is similar to the brushed DC motors. I haven't uploaded this pneumatic and hydraulic part. So it's about 168 slides. Perhaps when you need it, you can come and keep this file. You can get on-site training on that. But the main objectives for hydraulic and pneumatic actuators is because of the power density, okay? There's a dedicated book on this fluid power, okay, hydraulic control. So all this dedicated, and you see, this is a very old books, okay? Yeah, fluid, this is also 60, oh, gosh. Pneumatic system, also 60. So you can see today, you don't see a pneumatic and hydraulic system everywhere. But in some cases, you still see them. Say, for example, you have seen the garbage collection vehicle. So you have an arm and lift your garbage bin. So that mechanisms are all pneumatic, others are all hydraulic. So it's hard to believe you can use a motor. You cannot provide that level of torque at all. Then your motor has to be very big. Make sense? So that's the key difference between hydraulic system versus the electromagnetic system based on the motors, okay? So I want to show you this figure. We can stop today. It's called power density capabilities. So think about these numbers. For our usual motors, generators, those actuators made by motors, so they are limited by the magnetic field saturation. It doesn't matter you put lots of power, voltage or current in there. So the magnetization simply will saturate, remember? This is your B, this is your current. So it will saturate like this. So they produce up to per square inch, you can do 200 pounds, okay, 200 pounds. But so sometimes this is enough, but in many cases it's not enough. Say for example, what if you need a much higher torque, pounds per square inch? So this is like how many, like 1 order of magnitude, okay? It's 400 times, no, sorry, 40 times, okay, 40 times. So unfortunately, in many of the industrial applications, our nominal applications, so we like aircraft and so on and so forth, you need 1,000 pounds per square inch, okay? So in this case, motor is not usable. You have to use hydraulic or pneumatic. So anyway, so I have to stop here. We just have too many things to discuss. As I said, as I also promised, I'll prepare to review with you, walk through the last year's final exam. Get ready to ask questions. I'll open time for you to ask questions, okay? But before that, we probably will watch some of the video clips to know the PLC, DCS, LabVIEW. I think LabVIEW is very easy for you now because you are getting enough with Simulink. So we quickly go through some of that. Then next Wednesday, we're going to spend at least like 40 minutes, okay, on the reviewing our final exam side. So don't worry too much. If you did your homework seriously, you did your midterm seriously, also you check answers, so you have no problem, okay, you have no problem. Yes, transformers are used in like, okay, so where can we find answers for the hydraulic actuators questions on the quiz? I want you to read it. I'm going to upload that file for you to read it, okay? Should be very simple and very basic. You should be able to find it. Okay, next Friday, no class. I'll give you guys a bonus so you can focus on your homework and prepare your exam and doing your lab. All right, so that's the plan. If you insist, then we can have the class. Do you? I know everybody is willing to finish this class, but it's a long journey. I have to tell you, we never skip the class in the middle. So look at the YouTube playlist. We feel proud of ourselves. We have gone through so many things. And in the end of the class, at least I hope you psychologically feel that you are prepared much better than before for the job market. All right, so see you and have a good weekend. Take care. Bye-bye.